Okay, let's get started. Today we are going to talk about something defined by crustal deformation. It's mean that I'm going to have deformation in the rocks which located in the crust, and we are going to call it crustal deformation. And in order to study this, we need to understand what does it mean by structural geology. So structural geology is the study of stress and strain. Those who are taking strength of material, they are familiar with the stress and the strain. But here also I'm going to make it clear here again. So even if you don't get the concept of the stress and the strain from strength of material, I'm here to make it clear for you. So we said that today's topic is going to be about the crustal deformation. The deformation that is going to take place inside the crust. And in order to study this, it's mean that you are studying what's so-called structural geology. So structural geology, it's mean that you are studying the stress and the strain and any processes is going to cause them. And as a result, if you have stress strain, that means you are going to have deformation. And we need to understand what will happen to the rock after it's been subjected to stress and strain. So why studying the deformation of rocks is important for us as civil engineers? Well, in order to construct a dam or tunnel or multi-storied building, it's very important to learn, or it's very important to know the arrangement of rocks. Because if the arrangement of rock is weak, at some point, you may change the location of a dam or a location of a tunnel or a location of multi-storied building. And in order to do this, you need to have good knowledge in soil mechanics. In soil mechanics, you are going to study everything about the soil. And rock is going to be considered a type of soil. So the arrangement of soil is very important, and the structure of the soil, whether it's being subjected to stress and strain, is very important. In order to have a decision about the location of a dam or tunnel or any civil engineering projects, it's important to know the structure of the rock and the arrangement of the rock. Like you can see in the pictures here, you see a rock here and here and here, and it's clear that these rocks was subjected to stresses from the pictures, because we are seeing a lot of deformation inside the rocks. Today we are going to understand this type of deformation. But first, when we say deformation, it's a general term. It's not a specific, just general term. It refers to all changes in the shape and the position of a rock. So if you have changes or in the shape, or if you have changes in the position of the rock because of the stress, we are going to say we have deformation in general. And in order to have deformation, like I said, we need to have stress. And as you might have guessed, you will know that in order to have stresses, the stresses must occur at or near the plate boundaries. Why do you think these stresses going to take place at or near plate boundaries? Anyone can guess the answer?
Because of the type of the movements, they either go against
because
each
of the
other
type
or
of
go
the
apart.
movement.
Yes.
Yes, which means that you are going to have stress. So most of the deformation is going to take place at or near the plate boundaries. And if you have something like that, Here, as you can see, we have a group of rocks here, which is clearly, it has been subjected to stresses. And we call this, for example, if you have something like waves, condensed like wave like that, we are called this fault. And if you have fracture, like this one, and if you have relative movement, if you have fracture with relative movement, which means that the position of that point, it should be here. But when I have fracture like this one, plus relative movement, we are going to call this fault. So if you have a fault or fault, we are going to say that we have rock structure or geologic structure. So geologic structure are the features that result from the forces. So here we have features resulted from the forces. And we know that the forces, it has been generated by the interactions of tectonic plates. So faults and joints are geologic structure or rock structure. Okay? And in order to understand the stresses, I'm going to give you a simple example. First, we need to ask ourselves, why do we need the term stress? So mathematically, stress equal force over the cross-sectional area. If you are looking at this rod here, which is subjected to force F and so force F, and it has cross-sectional area. So the cross-sectional area here, it's mean the area which is perpendicular to the force. So the force is here, and that area is perpendicular to the force. So this one is going to be considered as cross-sectional area. So in order to calculate the stress, you need to know the force, and you need to know the structural, the cross-sectional area. So stress equal F over A. And the stress in the most of the textbook are referred to by the letter or the Greek letter sigma. So sigma equal F over A naught. F represent the force and A naught represent the cross-sectional area. Again, why stress is important? To understand this, assume that the maximum stress for this material here equals 3 megapascal. You know that megapascal, it's mean Newton per meter cube. If we are going to say that the maximum stress equals 3 megapascal, if the material is subjected to stress more than 3 megapascal, what will happen to the material? It will fail. Yes, it will fail, it will fracture, failure will take place. And if the material is subjected to stress lower than the maximum stress, lower than 3 megapascal, in that case, what will happen to the material? Will it fail or it will stay holding? The obvious answer is the material is not going to fail.
Yes.
Because the stress is lower than the maximum stress. So here, assume I have rod number 1 and rod number 2. And they are made from the same material with maximum stresses equals 3 megapascal. Okay, so I have rod 1 and rod 2. In rod 1, the force equal 100 Newton. In rod 2, we have the same force, which is 100 Newton. In rod 1, the area equal 50 millimeter square, while in rod 2, the area equal 25 millimeter square. So we have the same force, but we have same different area, different cross-sectional area. So which one is going to fail? Road 1 or road 2? And
Road 2,
why?
Doctor. Road 2.
Road 2 is going to fail.
Road 2, yes.
Why road 2 is going to fail? We have the same force.
No, but the area is different, and we have a rule called B equal F over A. When we have this big, I can say that. يعني دكتور إذا كان عندك
Yes, you are saying that you are going to calculate the stress here, and the stress here in road number 2 is higher than road number 1.
Yes,
that's what you're saying.
That's what I mean. Yes.
But why road number 2 is going to fail? You already proved that road number 2, it has higher level of stress than road number 1. But why road number 2 is going to fail?
Because it's more than 3 megapascal, it's going to be 4.
Yes, excellent. The stress here, if you calculate the stress here, you are going to say that sigma equal F over A. Then it will equal 100 Newton over 25 millimeter square. So the answer, it will be 4 megapascal. And 4 megapascal is higher than 3 megapascal, which means that road number 2 is subjected to stresses more than it can take. And as a result, failure will take place in road 2. If I'm going to define the material by the forces here, for example, if I wanted to buy some material, let's say you are going to buy steel, then will you ask about the force or the area, or I'm going to buy the material depends on its stresses, and why? Did you understand my question?
I will buy it according to the value of the stress that it can hold.
Why not the force?
Because the force may vary. It's not a problem if I know how much stress it can take. I can apply multiple values of the force on it.
Yes, that is the reason why. Because you cannot buy the material by the force, because maybe the material can take a lot of force, but the area is going to be very large, or the area could be very small. So we need a relation between the force and the area in order to buy the material, and that ratio is known as stress. So that is why stress is very important. I cannot buy a material by how much force it can take or how much area does it have, but I'm going to buy a material by stress, whatever the cross-sectional area. And it has been a practice for all civil engineers to buy materials by the stresses and the strain. So now we understand the concept of the stress, why we have stress, how to calculate the stress, why stress is very important. And the rocks is going to subject it to stress, and as a result we are going to have deformation. So stress is a force that deform rocks, and also when stresses acting on a rock exceed its strength, the rock will deform by flowing, flooding, fracturing, or faulting, which means that some kind of failure is going to take place because the stress is more than the its ultimate capacity. And we know that the magnitude of the stress is a function of the amount of the force applied to a given area. We already discussed this concept in the previous slide by the previous example. And we need to know that the stress, it could be uniform from all directions. For example, if you have cube like this one, the cube, of course, the cube, you can say any kind of material, but here mainly we are going to talk about the rock. So if you have a cube here made from rock, and it's subjected to stresses from all directions. The stresses here equal to stress here and here and here. In that case, we are going to say that we are having confining pressure. So confining pressure, it means the stress is uniformly distributed in all directions. And as a result, we are not going to have a change in the shape or the orientation of the rock body. The differential stresses, on the other hand, it means that you are going to have stress which is distributed unequally in different directions. So it means that if I have cube like this one, the stress in that direction is higher than that direction and or lower than that direction. The main point is the stresses in one direction is different than the stresses in the other direction. And in that case, we are going to say that we are having differential stress. So the stress, it could be confining or it could be differential. If it's equally distributed in all directions, we are going to say that we are going to have confining pressure. If it's distributed unequally in different directions, then we are going to say that we are having differential stress. And the differential stresses, it could be divided into three main categories. We have the compressional differential stress, we have tensional differential stress, we have shear differential stress. So the differential stress, it could be compressional stress, could be tensional stress, could be shear stress. So if you have compressional stress, that means I'm going to squeeze the rock. For example, if this one is a rock, by having forces in this direction and in that direction, I'm going to squeeze the rock, to compress the rock. And of course, as a result, the direction of the force here is going to be shorter than the other direction. So compressional stresses squeezes a rock and shortens a rock body. This dimension here is going to be shorter than the original length. The other type, which is tensional stresses, this one is opposite to compressional stress. Instead of squeezing something, we are stretching something. We are stretching the rock or pulls apart a rock until we have increase in the length in that direction here. So the original dimension or the original length is going to be increased, while in compressional stress, the original dimension is going to be decreased. The last one is the shear stress. In this process, we are going to have a motion in the top part of the rock. For example, I'm going to fix this part and I'm going to move that part because of the stress here. So we are going to have relative movement. This part is going to move relative to that part. So originally that point, it was here. And because of that stress at the top of the rock, that point, it moved from that point to that point. And if we are going to have something like that, we are going to call it shear stress. So shear stress produces a motion similar to slippage that occurs between individual playing cards when the top of the stack is moved relative to the bottom. It's just like you have the cards, you are going to move the top card relative to another. In that case, we are going to say that we have shear stress. So the differential stress, it could be compressional stress, it could be tensional stress, it could be shear stress. If it's compressional stress, that means the original length is going to be shorter. If I'm going to have tensional stress, in that case, the original length is going to be increased. If I'm going to have shear stress, the top point is going to move relative to another point. Any questions so far? Any questions so far? So let's move on. And like I said, if you have stress, it means that you are going to have strain. So strain means that I have a change in the shape caused by stress. When I have stress, I'm going to have a change in the shape of the rock, and we call this strain. So strained bodies lose their original configuration during the formation. So if you apply stress to a body or to a rock body, you are going to have deformation or a change in a shape. We call it strain. The deformation is a general term. Any changes in position, in the shape, it's deformation. But strain is a special type of deformation. So if you have something like that, and then you are going to apply stress in that surface. In other words, I'm going to apply shear stress. So if that surface moved relative to that surface, the top surface moved relative to the bottom surface. And assume here you draw a circle. And if that process took place, then what happened to the circle here? Did you notice the difference between the circle here in the beginning and after we apply shear stress?
Yes, deformation happened. Deformation
Yes.
in this size.
Instead of having circle, we are going to have ellipse. So we are going to measure the amount of the strain by how much the circle has been changed. So here is the idea of the strain. Now we understand what does it mean by stress, what does it mean by strain. And also we'll learn the confining pressure and the differential stresses. The last point, in order to understand the behavior of the rock, we need to understand the difference between elastic material, brittle material, and ductile deformation or ductile material. So also I know that those who took the strength of material course, they are familiar with the concept. But here we are going to explain the concept again so that we can understand the behavior of the rock. So we have elastic deformation, we have brittle deformation, and we have ductile deformation. So to understand this, please look at this picture or this figure. Assume that I have a material, and that material is fixed at that part, and also it's fixed from that part. And here we have the original length. So the original length is going to be referred by the letter L naught. Then I'm going to apply a force. I'm going to stretch that bar here or that rod. I'm going to stretch that rod from that direction and that direction, which means that I'm going to apply force. And this one is going to be tensional stresses. So as a result, like I said, when we apply stress, what will happen? We are going to have strain. So the strain is here in a form of increase in the length. So that length in the direction of the force is going to be longer, like you can see here. Then please focus with me. This is a very important point. If we are going to apply a force, and as a result, of course, if we apply a force here, it means that I have a strain. In order to get the value of the stress, I'm going to divide the force here over the cross-sectional area, which is perpendicular to the force. So I have a force, apply a force, which means that I applied stress, and as a result, I have increase in the length. If I have increase in the length, it means that I'm going to have a strain. So I have increase in the length. Then if I remove that force, what do you think will happen? I apply a force here, and as a result, I have increase in the length. If I remove this force, in other words, that force here is no longer working on that bar or that rod, what do you think will happen?
The material will go back to its original shape.
Yes, This one possibility.
Because it is in.
One possibility is that the material is going to get to its original shape. So if this one is L1, the material, it may go back to its original length, which is L0. We could have another possibilities. Like what?
The material will stay deformed?
The material could stay deformed. It's the other possibility. So if I stretch a bar, then if I remove the force, I have two possibilities. Either to get to its original length, or I could have new length. If I'm going to have new length, that means I exceed the elastic region. So as long as the material can get back to its original length, we are going to say that we have elastic deformation. So if you apply a stress to a rock, and if you release the stress or remove the stress, the rock, it will get back to its original shape. In that case, we are going to say that we are having elastic deformation. So the rock returns to nearly its original size and shape when the stress is removed. Is that point clear for you? Any questions about the elastic deformation?
Yes, Doctor, it's clear. Thank you.
So when stress is applied gradually, rocks initially respond by deforming elastically, which means that if I apply the force slowly, start by 1 Newton, 2 Newton, 3, 4, 5, we are going to have gradually response by increasing in the length. If I increase the force, then I'm going to have a response by increasing the length. And if I remove the force or the stress at any point, if it's get back to its original length, that means we are still in the elastic region or the elastic deformation. Now, we are going to look on the other possibility, which is we are going to have permanent deformation. And in order to, and that depends mainly on the behavior. Some material, it has brittle behavior, while the other, it has ductile behavior. So look at that picture here. We have small bar, and as you can see, we apply a force. And unfortunately, this time we didn't remove the force. We are going to stretch that bar until we catch or reach the ultimate capacity. We said that each and every material, it has a certain level of stress. If you exceed that level of the stress, the failure will take place. So, but we have two possibilities. The one possibility, when you reach the maximum capacity, of course, we are going to have increase in the length, but we are going to have a sudden failure without any signs, like this one. So the material here, it didn't show us any signs. It's just fail all of a sudden. We call this brittle deformation or brittle behavior. As a material could show a sign like this one, we call this one necking. It will going to show a sign before failure, and we are going to call this ductile deformation. In the ductile deformation, like you can see, before the failure or at the place of the maximum capacity for the stress, we are going to have deformation, large deformation actually, compared with the brittle material. Here, before the failure, we are going to have necking process like this one before the failure. If you are going to draw the behavior in terms of stress and strain, you are going to draw it or plot it in charts. you are going to say that assume that point is a point of failure. For the brittle material, when it's get to its maximum capacity, we are going to have sudden failure like this one. But in case of ductile behavior, when the material reach its maximum capacity, you are going to have large deformation compared with the stress. With a small stress, we are going to have large deformation. And this one is illustrated by that necking here. So if I'm going to have large deformation compared with the stresses after the material reaches maximum capacity, we are going to say that we are going to have ductile deformation. And if you have sudden failure like this one, without showing large deformation before failure, we are going to say that we are having brittle deformation. So once the elastic limit strength of the rock is suppressed, it's either bends, which means that ductile deformation, or breaks like the brittle deformation. Breaks like this one, or bend like that one, showing necking. So after the elastic limit, either to have ductile deformation or brittle deformation. So here we have a rock like this one. Like you can see, you have deformation, right? So how we are going to classify that deformation? Is it ductile deformation or brittle deformation, and why?
Doctor, is the image a cross-section area? Cross-section image?
This image here, it shows us the structure, the inside structure of the rock.
Okay.
So it's obviously the rock was subjected to stresses. And as a result, we have deformation inside the rock. So which one is this type of deformation? Is it ductile or is it brittle, and why?
My guess is ductile.
Why you said ductile? It's a good guess, but why?
Because there is
Curved
no
line?
break line, it's all curved line.
Yes, it means that I have bending, right? I have necking process here. If it's ductile, what do you think will happen?
There will be breaks line.
Yes, I'm going to have fractures instead of having bending like this one, because the material, it doesn't have the capacity to bend. So it's good you understand the ductile deformation and the brittle deformation. So before I move to the last point here today, do you have any questions about the difference between elastic behavior, brittle behavior, and ductile behavior? Does it make sense for all of you?
I have a question, Doctor.
Yes, please.
Usually we deal with, I remember, usually we deal with ductile and brittle with tensile stress. But do we apply the same concept for compression stress?
Applying the
compressional stress.
We are going to see this in the next section. Okay. Here we are going to see the if we have compressional stress and tensional stress and also shear stress. And we are going to say when we have brittle behavior, what will happen, and if we have ductile behavior, then what will happen. I'm going to go through that. Okay. Any other questions regarding the elastic, brittle, and ductile behavior? So let's move on. So I was talking about this here. So here in that row, we are going to say the behavior is brittle. And in that row, we are going to say the behavior is ductile. In that column, we are going to say the rock is going to be subjected to compressional stress. In that column, the rock is going to be subjected to tensional stress. and in that column, the rock is going to be subjected to shear stress. So, as you can see here, you talk about the compressional stress. So, if the material is brittle and it's subjected to compressional stress, in that case, we are going to have a break or fracture like this one with relative movement. And if the material was ductile, if it's subjected to compressional stress, then I'm going to have folding, which means that we are going to have bending like this one in shape of waves. Then, if the rock is subjected to tensional stresses, if it's brittle, then also I'm going to have fracture like this one with relative movement. If it's ductile, then I'm going to have stretching like this one. Did you understand the idea here? Did I answer your question?
Doctor, I have another question, if I may.
So I answer question, then I get other question. Good. Okay. Be my guest.
Doctor, our understanding of rocks that they are brittle material. How can rocks be ductile?
No. Also, I'm going to go through that point. So we have conditions. We have factors affecting the behavior of the rock. First, the factor is temperature. If I'm going to have higher temperature, the rocks tend to deform by ductile deformation. If you are having lower temperature, the rocks tend to deform by brittle deformation. Also, if your rock is subjected to confining pressure, then that also the rock would going to tend or to deform by the ductile deformation. I have other factors. The rock type itself, if it's made from igneous rock and some kind of metamorphic rock, the behavior tend to be brittle. And if it's made from sedimentary and some kind of metamorphic rocks, the behavior is going to be ductile deformation. Also, we have another factors for that. We have the time itself. Forces applied gradually over a long period of time generally result in ductile deformation. Did I answer your question?
Yes, Doctor.
So yeah, I'm happy that you asked question and already you are going to cover that points, which means that you are following the lecture, you are enjoying the lecture, which make me very happy. Okay, I'm going to stop here. Next time, we are going to discuss the different type of deformation like the joints, faults, floods, and we are going to have more information and more information about this type of the deformation. Okay, I'm going to stop here. Next time I'm going to pick up from here. Any other questions?